Hello, this is Math 2231 coming to you from the College of DuPage for summer 2020, and this lecture is entitled New Limits from Old, and the old is algebra and trigonometry. Let's dive right in. We're to evaluate the following limit or explain why it doesn't exist. So we have the limit here. So you know what to do. Let's see how you did. Now when you try plugging in x equal 2, you get 0 over 0. So that doesn't work. We know that's an indeterminate form. But what you can do in this case, and what you will think about doing often, is you will factor the top and bottom completely. And you see when the limit goes to x approaching 2, it never really gets to 2. So x minus 2 over x minus 2 is still a number. So those will cancel with each other. So this is the same thing as the limit as x tends to 2 of x plus 6 over x. And now we can just plug it in and we get 8 over 2 or 4 for our answer. Here's another problem. You're to evaluate this limit or declare and explain why it doesn't exist. You know what to do. Let's see how you did. Alright, so you try plugging it in, you get 0 over 0. Seems to be happening a lot, doesn't it? But now what we'll do is we'll do algebra on the top and algebra on the bottom. Now what we see is when we do the algebra on the top and we expand this, we get this expression. There is a middle term. We distribute and the 18s cancel out one with another, and we simplify it and we have this. So this was equal to this, and that's the same thing as this was the first thing, that was the last thing. So we're picking up here. But now we realize that we're talking about the limit as h goes to 0, but that never has h being 0. And so that means we can factor the h out of the top, and it will cancel with h in the bottom because h over h is always 1 because it never gets to 0. So when we cancel that common factor, we have this. Now you can just plug it in and you get the answer of negative 12. Here's another problem. You're to evaluate the following limit or explain why it doesn't exist. You know what to do. Let's see how you did. Well, here we're going to exploit one of our factoring identities, and that is we're going to remember that a plus b times a minus b is a squared minus b squared. And we're going to use a wonderful technique in mathematics, and that is multiplying by 1 in a clever way. So we start, this is the limit that we started with, but now we're going to multiply inside the limit by 1 in a clever way. So we take this factor over this factor, and notice that this is the conjugate of the first factor. So you see it is a minus b times a plus b in the numerator. So that is going to be t squared minus, this is going to be the square root of 3t plus 4 whole squared all over this. So you see we've simplified things, and now I can simplify further by doing some algebra, and I get that the numerator is t squared minus 3t minus 4. Now that will factor, so I factor the numerator and I factor it and I get this. Now I don't have exactly a common factor, but I have almost a common factor because t minus 4 is 1 times the quantity 4 minus t. And so when I cancel this with this, because you see this is the limit as t tends to 4, it never gets to 4. So those are just numbers over numbers that are always minus 1. So I will cancel these, but I will have a minus 1 there. And now once I cancel out that factor, I can just plug it in, and my answer is minus 5 over 8. These are important techniques that we are learning. Given this function, it's a piecewise continuous function, you find these limits. The limit is y tends to 6, and the limit is y tends to minus 2 of g of y. You know what to do. Let's see how you did. Okay, so the limit is y tends to 6. We're going to use this part of the definition, and that's to just plug it in as minus 17. When you're tending to 2 from the left, minus 2 from the left, you have one definition. When you tend to minus 2 from the right, you have a different definition. You plug them in, and one side you're going to get 9, the other side you're going to get 7. The limit from the left does not equal the limit from the right. That means the limit does not exist, and we have explained why. So the answer is does not exist, and that is why. Here's another piecewise defined function. The function is different this time, though. Let's see how you did. You get the same answer from both sides, and that was an if and only if, so that means the limit is equal to 9. Here's a fact. We could call it a theorem, but if f of x is less than or equal to g of x for all x on a closed interval a, b, except at x equals c, where c is a point within that closed interval, then the limit of f of x is less than or equal to the limit as this happens. It's important that you realize this is less than or equal to. There's even a broader statement that we will talk about, which is called the squeeze theorem. And here we have, suppose that for all x on AB, except possibly at x equals c, because again, we don't care what happens at x equals c, we only care what happens near x equal to c. We have a function h of x that's caught between f of x and g of x. And also suppose that the limit as x tends to c of f of x is the same, L, as the limit as x tends to c of g of x. So g of x tends to L and f of x tends to L for some c in there. Then what happens is two things. First of all, the limit as x tends to c of h of x, the thing that's inside, has to exist. And moreover, a second thing is it has to equal L. Here's a picture. So you see the purple function is h, the red one is g, and that is this. So you see they're pinching or they're squeezing this down. So since h of x is between the two of them, it has no choice but to converge, is the word we use, to the same limit point, and that is L. All right, now we have to evaluate this following limit. This is limit as x tends to 0 of x squared times cosine of 1 over x. Let's see how you did. Well, one thing that we know is that the cosine function of x is always between -1 and 1. And that means even if I put 1 over x in there, it would be between -1 and 1. And I don't worry about this not being 0 because in the limit, we're never letting it be 0. So we're going to take this expression and we're going to multiply all the way through by x squared. So when we do that, we will get minus x squared here. We'll get x squared cosine 1 over x here, just like we did. And we're going to get x squared here. Now the limit of this, as x goes to 0, is 0. And the limit of this one, as x goes to, excuse me, I did that the wrong way. The limit of both endpoints are 0, and so the one in the middle, by the squeeze theorem, because we proved that it was always between there, must also be 0. And here you can see what happens with the graphs. See you in Lecture 8.1.